Monsieur Spiwack, vous avez 45 minutes pour nous exposer vos travaux.
Thank you and welcome everyone. So I'll be talking about Coq and Tops, and giving a bit of context. Coq stems from a history of type theory initiated by De Bruyne and Martinez independently for different reasons. Two motivation and one solutions, that's a pretty good sign usually. So what it amounts to is a foundation of mathematics where computation has a part to play. And later on, works especially by Thierry Coquin and Christine Paulin, works at expanding the computational power of type theory and gave birth to what is now known as Coq. So, more precisely, dependent type theory are a kind of type functional programming language which has a particular kind of type called dependent type. Types that depend on values or programs. So here is an example, the type of lists of size n, which reads a list of size 0 is necessarily the empty list, there's only one, and a list of size n plus 1 is the data of an n and of a list of size n, where a is a parameter of that very slide. There are two ways to make use of such type. The first one is called dependent product or pi type. It's the type of functions. This one reads a function that takes an n and an a and returns a list of size n. And in this particular case, the function is that which returns the constant list, but this was only the a over. The other way is the dependent sums or sigma type, which are the type of pairs. In this case, the type or the data of an n and a list of size n, which amounts to say this is the type of list, tree of list, or the type, or the size, sorry, and with the addition that we have a direct access to the size. To make a foundation of mathematics of this programming language, we read the statement x as type A as x is a proof of A. And then the logical connective are interpreted as particular type constructions. In particular, the disjunction is interpreted as the type sum. That means that a proof of A or B is a program that computes either a proof of A or a proof of B and tells which. Also, a proof of A implies B will be a program that takes a proof of A and returns a proof of B. And this is more or less the very definition of constructive logics, which means that the dependent type theories are naturally constructive, and Coq is as well. So what we're going to do is take advantage of this duality between programs and proofs. On the one hand, we can read dependent type theories as foundationless computation, as I was saying earlier, but we can also see them as functional programming languages, where we can do some verification, some formal verification. And we're going to try and adopt a point of view that is at the intersection of these two sides. And what I'm trying to advertise as a style today can be seen from a programmer's perspective as writing programs interleaved with mathematics. But from a mathematician perspective, it can be also seen as writing constructive proofs whose computational content is efficient. So we're going to do that using homological algebra as a test case. I'll explain why later. And we want to see when Coq stops to support this particular style of programming or doing mathematics. To do that, I first take the point of view of the programmer and take this title apart and start with the word verified. Here is a small and straightforward Coq program, the Fibonacci sequence. Which computes the Fibonacci sequence. So there's, as an example, a field of 18, which is 4181. So, okay, this computes, but this is really inefficient because it will compute the same numbers over and over again, and Fibonacci numbers are big. So we want to do something better. So let's take another algorithm first. computes the Fibonacci sequence using fast exponentiation of 2 times 2 matrices. It's a far clever algorithm, and it's also a far bigger program. And what I just said, it computes the Fibonacci sequence, can be stated otherwise. It is the same program as the previous one. Well, it computes the same values as the previous one, which is more straightforward. The problem is that, well, of course, this is a fairly small program, so you can convince one yourself that it is true. Though actually it is not, because I did something wrong somewhere. I mean, I've been sloppy. There should be red on this side, but it doesn't appear because of the projector. But I've been slopping the 4th cell of the matrix product, which is a copy of the 2nd cell instead of being changed. So if you replace 2 1s by 2 2s, that will give us the right program. The point I'm trying to make here is that a statement of the form, this program does that, is really hard to read for a human being. We're not made to read statements that need to be very precise, with keep other mistakes. Computer don't. But it's only natural here to call the computer to the rescue and to ask it to verify a proof for us that Fiben is actually the same thing as not Fiben. So a theme that will come back is that verification has all to do with efficiency. It's because we need efficiency that we write a difficult program and we need to verify them. So the next step on that path is to choose good data structure, and that will be the word computation. Here is the first data structure, natural numbers. That's what we use for Fibonacci sequence. So here is a straightforward definition that works in Coq, saying that, that 0 is a natural number, and that if n is a natural number, then s of n is also a natural number. And that's all there is. Below, I've written the memory representation of these numbers for 0, 1, and 2. The thing that is important in these diagrams is that the arrows are the thing that cost. Arrows are pointers that's following an arrow is costly, and that's about it. The rest is cheap. That's what I mean. And so it should be pretty clear with this slide that n here is represented by n arrow chains. So that will be a pretty inefficient data structure. The far more clever one, still in Coq, would be that one, where we use the binary representation of natural numbers to encode them. And here we only have a logarithm of arrows. It already shows on 2 that it's more compact than the previous one, but I threw in 18 because it was possible, and it was not nearly possible in the previous slide. But that's, if that's an improvement, that's way below the performance of usual programming languages. Usual programming languages use a data representation like this. Granted, there's not all natural numbers here, only 2 to the n, but at least there's no arrow at all in them. It's very compact, and additionally, computer processors are very good at summing and multiplying and other things on these sort of numbers. So we'd like to leverage that, but there's no real way to do that inside Coq, because Coq doesn't know about memory or about processors. So we have to add that additionally. It had never been done properly for historical reasons, because the initial motivation for Coq was still mathematics. And it was more important to have good mathematics sometimes than having the most efficient possible program. Another reason is that since Coq allows us to verify the program, there's much more that Coq needs to know about these integers than a normal programming language. And so if we do that the straightforward way, we add a black box and a couple of operations on this black box, then there's pieces of code everywhere in Coq that have to be modified to be made aware of the existence of these new operations. In particular, we want to prove things about them, otherwise we can't verify anymore, so we're getting off point. And to do that, we have to provide Coq with everything that is true about these integers, like the fact that addition is commutative, or associative. So I added them nonetheless, but I went for a much more lightweight approach, which is to say I took a Coq representation of the same kind of data, and I modified only the compiler of Coq, so that this data type is compiled into the intended representation that we showed earlier without any error, and so computation can be efficient. So I said I modified only the compiler, so that's already something, and also I don't need to give any new property to Coq. I just need to prove more that everything is already here. It knows everything there is to know about this representation. So to give an idea of how important it is to modify, to add this sort of data type, I'll talk about Coq Prime a little, a project by Laurent Thierry and Benjamin Grégoire, which aimed at proving the primality of some of the natural numbers in Coq. And without matching integers, they managed to prove the primality of numbers up to something of the order of magnitude of 2 to the power of 40,000. That's six digits. 5 digits on the top. 2 to the power of 40,000, which is big. But with the integers, the machine integers, they were able to prove the primality of a number of the order of magnitude of 2 to the power of 200,000. That's 5 times as many digits in the decimal representation. That's really, really, really big. So, as I was saying, well, we have to. The problem of data representation is very important, and it's going to be a focus for the rest of this presentation, and not only at low level, but also in general, finding good representation, and that will be the word algebra, where I will talk of mathematics in general. The first example, and I'm still a programmer, comes from OCaml's standard library. So that's fairly mainstream programming and fairly concrete motivation. We wanted to define a particular kind of predicates that I've represented in set expansions here. They are finite predicates that are true. They are true on a finite number of things and false on everything else. And they are built piecewise. For efficiency reasons, they are represented as AVL trees. And what's interesting here is that if I build, depending on how I build my predicate piecewise, I will get different trees. For instance, here, the predicate that is true on 3, 5, and 7 has a different representation than the predicate that is true on 5, 7, and 3, though we intend them to represent the same predicate. So when we will try to prove something about programs using these, we will work mentally with a notion of equality or observation that is different from the equality of representations. This leads to the idea of set introduced by Bishop. And what's very interesting in something like Coq, and let's be the mathematician for a minute, is that with dependent types, I can certainly work explicitly with this equality rather than keeping it in my head. So here is the definition. A set is a type and an equality on that type. For those who know Coq, bear in mind that this is not the set that is a keyword in Coq. I couldn't find a better way to write that in a non-confusing way, but that will be a set for us. And let's forget about Coq set, which I renamed when I wrote that in Coq. So when we have this sort of set, of course, we will restrict the kind of programs that we will consider meaningful. We will only want programs that respect the equality, map equal element of a set to equal element of another set. So this is the role played by the functions, that's how we'll call them, these sort of programs. And the equality here is a Q overhead, but in an infix notation. Finally, about this idea of having an equality like that on the side, this can be installed in an old dichotomy between extensionality and intentionality. So in this dichotomy, sets in Bishop's sense would be the extensional way to go. The intentional approach, which is used successfully by projects like mathematical components, would be to take an equality a priori and then shape the data representation so that the intended meaning is reflected by the equality. So in this case, the intended meaning shapes the data representation, whereas in the exceptional case, it shapes the equality. And my point is that the intentional approach on that works as long as we don't care for efficiency. Because data representation matters. But moving on to a slightly different subject, still on sets, but a small intermediate. So let's take something like that. I want to prove properties about sets. Properties such that, I don't know, there exists a set such that P. So I want to do that in Coq, of course, because I don't trust my pen and paper proofs anymore. And Coq tells me, well, to prove that, what you have to do is prove this. And this second line reads as, give me an x and prove that P of x. And that's pretty much the same as the first one. We didn't get much help here. Of course, we can use properties, other properties, but basically it comes to that. What it means here is that when I want to give that set, well, I don't have access to automation procedures to prove anything inside the definition of set. In particular, I can't use automated procedures to prove that a Q is an equivalence, which I usually want to do. Rather, I would write something like that most of the time, or at least some of the time. It's not very different, but now we have two statements to prove. One is, give me a set. And the other one is, well, this set was x, and prove that P of x. And these sort of dependencies between the proof of a sub-goal and the statement of another one couldn't be handled by the data type used to represent proofs in Coq. By the way, since I'm going to use this vocabulary again, these sort of proof transformations are often called true refinement in the community of Coq. And so, to be maybe more convincing, I will introduce another piece of data, well, another brick of the mathematics as a construct, which is category. If category was used, and if sets, were used to infuse meaning into types, category will be a practical tool to help us abstract away low-level details. That's a very common scheme in programming. And when doing mathematics with a computer, it becomes necessary as well. So this short aside done, I think it's arguable that it's a fairly more complicated definition than sets. So now, maybe imagine you want to prove this property without any automation. Well, at least not any automation to provide the x. That's pretty annoying. So I did the work to modify Coq so that it could handle this sort of proof transformations or statement transformations. This was hard because there's a big amount of code in Coq that actually depended on the precise representation of proofs and proof steps, that we call tactics. So this prompted me to introduce an abstract interface for these type of proofs and tactics. so that the next one that wants to modify it don't get as many headaches. So just a few words on this abstract interface. It's monadic to express the dependencies or the sequentiality between tactics, and also that way it can be read, Emoji style, as a small programming language whose effects are to modify the current statement and to advance in the proof. So it's built around true refinement, and maybe more anecdotically, I was later able to add support for other features like backtracking. And interestingly enough, that's a slightly smaller code than used to be used for the same purpose. So now I just keep being the mathematician for a while and introduce the idea of efficient mathematics. To do that, I'll do a small detour with the principle of choice, which is a familiar notion that can be stated in many ways. The way that I will be interested today is if f is a surjective function, and I recall that a function is a program that respects set equality for us. So if f is such a surjective function, there is another function g such that g compared with f is 1. That's f round g in the usual order. 1 is the identity. I'm getting a bit confused here, but let's focus. So here on the bottom of the slide, I've got two sets. Each of the back contains crosses, which are different data representations, and the one on the right contains a line which represents two equal representations. So let's take a function and call it blue. So this blue function is surjective, so it verifies the premise of the principle of choice. Now, in constructive mathematics, when you have a surjective function like that, we can deduce from it a program that goes the other way. Like that, let's call it red. So it's black, isn't it? Never mind. So let's call it black instead. And black is a program, but what I want to stress out is that it's not a function, because it maps the line on the right to no line on the left. And that's precisely what functions don't do. And actually, we can prove that if choice is verified in a category of Bishop sets, then we can build a program that can't exist. But that leads us to unit choice. It's a very degenerate version of choice, which can be read many ways. Two of these are functional relations are functions, and the other way is functions that are bijective are invertible. It's pervasively true in mathematics. It's true in traditional mathematics because functions are simply defined as being functional relations. It's also true in Bishop set theory because the fact that f is injective prevents the case from the previous slide where a non-line was mapped to a line by the blue function. But I argue that it's not that a good thing, that much of a good thing. So let's take an example, a cyclic group generated by G. And the exponentiation of G gives us an example of a bijective function. It's both injective and surjective by definition. But the reverse problem, which is called the discrete logarithm, happens to be a very hard problem. There's no known efficient program that computes a discrete logarithm. And actually, the Diffie-Hellman key exchange protocol relies on the fact that none should exist. So in view of this example, in the light of this example, I think you can say that unit choice is a very powerful oracle to produce very inefficient functions. It's not being helpful. So there's basically two ways to work with that. First way is to say, well, we'll just make sure that every single proof we write have an efficient computational content. In which case, there won't be many cyclic groups, or not many that you will like. I find that a bit restrictive. And the other way, the one that I followed, was to just drop the unique choice altogether, to work without it, to develop mathematics without unique choice. So it has a few interesting consequences. The first one is that it sort of mechanically splits proofs into two parts. A part that will be executed and that needs to be done efficiently with care, and parts that will be purely static, that are only used as typing informations of the sort. And these parts don't need to have an efficient computational content. And this separation appears in the formula already. We have, in particular, two kinds of existential statements. The first one is the subset statement, where we get elements of set A accessible, and we compute them, and we compute with them. And the other one is the existential statement, where the X cannot be used for programs. An interesting mathematical consequence of that is that we cannot have a topos of sets, because topo always validate the principle of unique choice. Instead, there is a slightly weaker structure called quasi-topos. And this was, and I've proven part of it in COB already. So I think it's time enough to speak a bit about homological algebra. I announced in the second slide or so. So why homological algebra first? It is because it was a good test case, in particular because of the work of Francis Saint-Girard and others, including Julio here, which has two parts. One part is a program, Kenzo, that computes properties of homology groups, and happens to be written in Common Lisp and be mostly functional. As Coq is only functional, this was a pretty good start. And the other part is a version of homological algebraic theory called effective homology that supports the computation done by Kenzo, but is purely pen and paper, and happens to be constructed. Here again, good match with Coq. So, it's time to say what homological algebra is. So it's many things, but for today, it will be only what fits on this slide. So let's take three abelian groups A, B, and C, and morphisms F and G between them, such that F and G happens to have a null composite. In this case, the image of F is a subgroup of the kernel of G. So we can take the quotient. We call it H, the homology group of F and G. And the problem in homological algebra will then be to compute a good presentation for this group, or a good representation in general, or any property about it. And that's it, except that we will usually replace abelian group by something more general, like R modules on a particular ring R, or something even more general, that will be the next slide. And usually, there will be an infinite amount of morphisms, and this whole structure, infinite structure here, will be called a chain complex. That's the main object of study. So, the next slide was slightly more general than modules. Abelian categories are really one of the motivations for introducing category in the first place. Abelian categories are a particular kind of category that have properties that we're familiar with when working with linear algebra. So, in particular, the home sets have an abelian group structure. It also has a direct sum on objects, and kernels, also cokernels that are another way to state the notion of taking the quotient of a codomain by an image And finally, it has this all familiar property as well, that subobjects happen to be, well, every subobject can be presented as the kernel of some array. Right, and this is the last word of the title, and it's in, it doesn't matter, but it tells us that it's time to wrap everything up, and to put everything together, and especially to speak about homological algebra without unique choice. And the first thing we encounter is that abelian groups are not an abelian category. You need the unique choice to prove that. But instead, it is what's called a pre-abelian category, not very studied in mathematics, usually just as an intermediate step in building abelian categories. So pre-abelian categories are just like abelian categories, except that the fact that subobjects are kernels is not true anymore. And similarly for kernels. And what I found very interesting about that is that when starting to work with pre-abelian categories instead of abelian categories, I developed naturally idioms that were very similar to what we can read when reading about effective homology, which has no category altogether. Well, no category at all, I should say. Never mind. So, just a bit of example, I wanted to write a program using this technology. So this program is a fairly simple one that computes with the following efficient statement. I mean efficient because I shape it so that the proofs can be controlled. Now, if I take a linear function between two finite dimension vector space, then the kernel is finite dimensional. So I did all that in the language of pre-abelian category, especially modeled what it means to be a field, in the pre-abelian language, and then was able to test it on various matrices. So here, the example I showed on the slide is the matrix that reads 1, 2, 3, 4, 5, etc. It's 40 by 40. So you'll be happy to know that this matrix has a kernel of dimension 38. I could have put a basis as well, but it was too big for the slide. So I skipped it. But back to homology. Homology can be easily defined in the language of pre-abelian categories. Actually, it's pretty much what I said earlier. So we take three objects A, B, and C, F and G morphisms, with null composite. So the first difference is that the kernel is now explicitly on the diagram. The universal property of kernel tells us that since F and G has null composite, then I can lift F to a function F prime, whose codomain is care of G. Now, what I want to do is take the quotient of the kernel of G by the image of F, which is also the image of F prime. And I said earlier that it was precisely what the kernel does. So here we are. H is the co-kernel of F prime. But I said the object of study, the main object of study were chain complexes like that. I'd like to argue in the next few minutes that it's actually a particular case of what I've shown on the previous slide. So to see that, let's just drop all the arrows here. We only have objects, infinitely many of them. We call that a graded object. We'll take a second graded object, and we can build maps between these, like that. That gives us a category, actually a pre-abelian category. And all the pre-abelian operations are done pointwise. Good start, but that's not enough, because we cannot represent an object like that with only arrows like that. What we need is sloped arrows, a bit like this. The slope is generally called the degree of the morphism. When we have morphism that can be sloped, then we still have, it's still pre-abelian, it still works, and we can now see a chain complex as a graded object with an endomorphism D of degree -1, such that D composed with itself is null, and such that and then the homology groups can be recovered from the homology object of D and D. So that's it, except I lied a little, because this doesn't make a category anymore, not quite. The reason being that I cannot sum I can sum morphisms of different degrees, morphisms of degree 1 and morphisms of degree 0, for instance. It just doesn't make sense. So all of these morphisms, for each degree, they live in a different word, in a different abelian group, which are homosets. That leads to a slight generalization of category called graded category, whose definition is here. It's parameterized by a monolith, and homosets are not only indexed by a pair of objects A and B, but also by an element of this monolith. And the neutral element is used to define the identity morphism, and the multiplication is used to define the composition of morphisms. So with that in mind, we can state a nice theorem, this one. If I have an n-graded pre-abelian category, then the category of all its graded objects is n times that graded and is pre-abelian. And this is the precise way to say that the infinite case is a particular case, yes, of the finite one. So this is important for us. That adds a lot of cost sharing, but it doesn't quite work in Coq. So here we reach the limit I was talking about at the beginning of the talk. I explained. So we have two different morphisms. One composed with F, one is the identity morphism, and F. They are supposed to be equal, but first they have different types. Home of E times D, where E is the neutral element, and home of D. These are two different types, and actually there's no way to tell Coq they are the same. It's just not possible. So you can't even state the property that one composed of F is F. So of course I tried a few workarounds with some slightly different version of equality or different definition of graded category. But I found none of them to be satisfactory or to actually work without cluttering the code beyond the usability. So here we are. That's the limit. That's where we stop being held by Coq. And that was the end of the talk, so I'd like to wrap it up. We've talked about adding natural integers for efficiency reasons, and efficiency problems also prompted us to deal with dependent types and change the interface of proof and tactics. And I gave a natural interface for that. From a mathematical point of view, efficiency was very much tied to dropping the unit choice with interesting mathematical consequences. And finally, I hope I convinced you that graded categories can be used as a very useful programming pattern for homology, but it doesn't quite work in Coq. Thank you very much.
Okay, thank you. So we now have questions by the members of the jury. We start with Claudio.
Okay. First of all, I must say I really appreciated the beginning of this. It's very nicely written. You have been able to hide all the gory case, so that it gives a nice picture. Maybe you added them a little bit too much in some situations, so I would like to ask some questions on this point. So the first one, the first question is a little bit more philosophical in nature. So it's, in a sense, the interesting part of your approach is that you are looking at mathematics, but from the point of view of a computer scientist. So you really care about efficiency, about generalization, about the facts that you are avoiding, the action of unique choice, is exactly motivated in the thesis because of this, because we are saying I want all my functions to be somehow efficient, and the action of unique choice gives me functions that have no control on the efficiency. So, so my first question is, well, there would be another possibility, of course, instead of avoiding the action of unique choice, you could change your logic, adopting some kind of light logic or something like that, so that the proofs that you can find can only give you efficient inverse functions, or that or have some kind of modifiers in the logic, so that you can know if a proof has an efficient inverse content or not. So, what do you think about this in general?
So I'll try not to be too long, because there's a lot of things to say about that. Firstly, we cannot equate being efficient with being polynomial time. Efficiency is a practical notion. Sometimes the exponential algorithms are very fast in practice, as the case for SAT solvers, for instance. So I don't think it's quite reasonable to put a bound on the time complexity within the logic, because if we prevent some perfectly legitimate and efficient programs to be written, and I'd say efficiency is more a problem of control. It's that I want to know what I'm doing, and I want to be able to model the computation in my head, at least a bit, to get an idea of what is giving me a good performance and what is not. So the question was about, having a logic that tells me when I've been efficient or when I've not. Well, that's mostly the same thing as dropping the unique choice. That's what I do. I just separate the logic into phases. Of course, whatever is efficient can be considered inefficient. It doesn't matter. It's just the only way that doesn't work. If I want to write something efficient, I just have to specify that it's a formula in the formula, in the type of this program, that which part of the program I intend to use, and the other one, I just don't speak about them. Of course, a computer can't do that in my stead, because it's really a matter of control. That's really a human factor here. So that's what's crossed my mind right now. Does that answer your question? Yeah.
So the second question is still on this topic somehow. So to avoid the action of unique choice, you are using the pop universe.
Yeah.
And we know that inside pop you can also have classical logic and
yes.
to the middle. While it seems to me that in the thesis you stick to having constructive logic everywhere, even in those fragments. So can you say something about it? Why do you think it is proper not to have classical logic in that part?
Just because I like constructive mathematics better. I don't think there's any, at this point, I can't say there's any foundational reason to choose one over the other. Fundamental, practical reasons. I like working with constructive mathematics myself, so I stick to it. Some people might like to add classical logic, and it would work as well. Actually, I did that occasionally where I wanted to prove that something was incompatible with my mathematics without unique choice. Because when I add classical logic, then suddenly I can make a lot more programs using unique choice or slightly weaker versions of it. Actually, classical logic is not compatible with the unique choice because it makes the similar kind of programs that decide the validity of propositions. So yeah, there's not much to say. The fact is, dropping the unique choice allows us to use classical logics, but I didn't want to.
So let's move to the second part of the thesis, the one where you change the implementation of code. So I will focus on the second change, so the one about the change of data types and presentation for proofs, presentation for text, and that's it. So looking at what you write, everything seems very nice, it worked very well, but I expect that when in practice you did all the job on modifying the code to use these things, you faced many kind of difficulties. So the first question is, can you talk a bit about the kind of things that were difficult to do?
Yes, there's still a branch on Coq SVN repository called New Proofs, on which you can read my SVN logs from my first tries at that, and they couldn't be read as a series of laments, so that explains a bit how I felt then. That said, well, it's just that it's very heavy. So when I change something a bit deep in Coq, I can expect to have absolutely unexpected bugs in things that are seemingly unrelated to what I change. And we had a lot of efficiency problems at first as well, because some structure went bigger. So I can't be very concrete. I mean, it's been a day-to-day task of making things and going to people and asking them, what do you want in this new thing? I'm doing something new, I'd like to do it right. So by the sections between trying to do something and asking other people what they wanted to do, then it became clear that the monadic interface was pretty reasonable. This particular part was not too hard. It's really about plugging the existing onto the new system that was really painful and usually often done wrong, actually. It doesn't.
Yeah, I'm not. Let's say I'm not really fully convinced. So I think that a lot of the problems comes from the fact that you are plugging something on an existing system, so you have to adapt different things and so on. But I think
solutions as well.
Yeah, but I think that you probably faced also problems, for instance, of efficiency that are not related to plugging to the system, but the way you implement stuff. That's the presentation of.
Yeah. We did because so speaking technically, the type of proofs moved from being something specific to being a more general useful types in code called overmap, and this type happened to be used pervasively, and in particular, so they are avial trees, and in particular there was lots of pieces of code that would walk through them linearly, so walk through every single of its node, which was fine when they were like 20 or 30 nodes maximum, but now we reached 20,000 nodes in some proofs, so that made some benchmarks simply explode. So there are other efficiency things that we probably will face later when we manage to play at bigger level with the backtracking, because we don't want to backtrack between goals that cannot influence one another. If we do that, and at the current time we do, we can get pretty bad behaviors as well. But apart from that, I don't think there was a lot of problems. The new implementation is more or less as efficient as the other one. It's a bit magical. It mostly didn't change anything. I thought it would have in one direction or the other. Only a few benchmarks went really ballistic. Apart from that, it was pretty much as before, surprisingly. There's probably still more to come.
And finally, what are the? Do you see any effects of the user interface of the system that your changes can have? Like, I don't know, the possibility of having tactics that work in parallel on many goals, but not just iterating over the goals, but considering a set of goals as a whole.
Yeah, that can be done.
For instance, having the execution of tactics split up in small steps, so you can end and stop inside tacticals, and in particular, how that combines with very hacking.
Yeah, so I did a particular choice on that, but there are many ways to think about that, I believe. But I didn't take the mathematical approach at all. The tactics are considered as a whole, and they can't be split. So backtracking happens in tactics. And when you reach a dot, then you throw the backtracking stack and keep the result through here. To have a small step execution, I haven't documented that in thesis actually, but I've built a new mechanism for focusing and use that as a way to walk through proofs. And since we can now build proof that works on all the open goals, the idea is instead of writing A, comma B, and executing A first, stopping at the comma, or the semicolon rather, and then executing B on all the subgoals, what this adversarial style is to say, let's focus on A, on the first goal, sorry, apply A, then we'll have 2, 3 new subgoals, and apply B to all of them. And that's pretty much the same, except that backtracking backtracking doesn't happen behind these two tactics, these two steps. So that's the point of view I took, is that backtracking happens in black boxes, and dots stops backtracking, and I use that for splitting tactics with focusing. So time will tell which of the approach is better. I really don't.
Okay, I think I'm satisfied.
Okay. Uriel? Okay. So, first, I want to say that your work is very wide. It's dealing with very different things, from category theory and homological algebra to very, very technical points in compilation, Coq, type theory, etc. So it's a first good property of your work. It's very nice. I learned a lot reading the memoir. And you saw that you can present the results in a very different way. The oral presentation is very different from the written presentation. It's a good sign that the work is very rich. So my congratulations for your work. And I am, for the questions, I am focusing on my part, like homological algebra. I have 2 questions related to the possibilities, to the other ways deal with in the memo. The first one is about do you think that there is some problem, type theoretical problem with the working with free abelian groups in general, with other free abelian groups, with taking as generators a Bisopian set?
Right. No.
No problem.
No, there's no problem.
Because you focus on the computational part, so with the finite dimension stuff to work with the kernel and so on, but there are other part of the effective homology theory dealing with infinite dimensional spaces and so on.
Yeah, but no, I don't. Yeah, the free. It's perfectly possible to define the free group over an abelian. No, the free group over, or the free abelian group over a set. It's pretty much as you can imagine. It's just like this, and then quotient sets are very good at quotienting. So. No.
Yes.
No problem.
So the other question is, you find a problem with the graded case. This is the natural way of working with chain complexes and so on. But the question is, exactly as the other question, do you think that there is some problem from the type theory to deal with with chain complexes, I mean, without, in the ungraded case, without grade.
You mean like a differential object?
Yes, a differential object.
No, differential objects are pretty straightforward. I could have proved the DPL for
Yes,
instance
yes,
on them,
yes.
but I didn't do that because Jesus did that before me.
Yes.
And I was more interested in trying to pass the general case and see how it worked. My point was actually that I wanted to be able to state the graded case as an instance of the differential object thing, where the object is taken to being a graded object and the array is graded as. That was the goal. In the ungraded case, there's no dependent types that appear at this particular stage. So it's pretty straightforward. You just have to do some rewriting.
Yes, but there is again there is infinite series there.
Yes, and so here is so constructively saying that a function will be locally idempotent, oh, no, nilpotent, sorry. That was the part of the statement would be to state in a certain way that computing phi and psi will terminate. So it will be a certificate of termination of that. So in a certain sense, the main difficulty is stating, finding a proper way to state f is locally nilpotent. And that's not very hard. You would use the ACC predicate or a similar thing from Chrome.
So, keeping apart the problems with the degrees, you think that all the theory could be developed?
Well, I think it's it would not be much. It wouldn't be harder than in Isabel than what Jesus did to do the same in Coq, I think. From this point of view, from the point of view of pre-abelian categories.
But what about the principle of unique choice?
No, we don't need it. I do believe that in a certain way, when Francis you and others wrote effective homology, you did away with the unique choice without knowing it. But it was, I mean, you don't use it, really, or pretty rarely. So it's not that we show this problem when importing effective homology.
So that means that there is a theorem saying that all the effective homology can be written in the pre-abelian category. Someday you are claiming that. Okay.
I'm sure most of it. Of course, so our conjecture is that at some point we go back to the abelian word because presumably the category of finitely presented abelian groups happens to be abelian, and that's probably important.
Sorry, and that?
What?
Sorry.
I said that the finitely presented abelian groups, so that's our conjecture, should be an abelian category even without the unique choice. And we suppose that it is important for homology and computation with homology. We're not sure at this point, but that's
but you know that infinitely presented groups are important too.
Yes, but you won't compute the same way with them, and that's the whole thing. Yes, the two words will coexist at different stages.
Two layers. Okay. That's all. Really?
Now back.
Okay. So I would like to join the others in the congratulations. It's a very nice thesis. Indeed, it was a pleasure to read. I remember that some 8 years ago, Jerry found this manuscript by Francis Gerard about this constructive algebraic topology, and he was excited about this, but didn't have anyone to actually work on it yet. And then you started this, and it's, I think it has worked out very well. Very nice. I have some specific points. One is this was partially covered by Claudio already, but one was already partially asked by Claudio, but I want to rephrase it a little. seems that you got this problem by deviating from the Martin-Love interpretation of the Curry-Howard interpretation. If you would have used propositions as types, then the problem would have disappeared. There are reasons for this, among mainly the efficient one.
I'm not sure what you're trying to mean. Are you trying to mean that I would, well, in the propositionist type thing, in ITT, unique choice is validated, if I interpret mine.
Correct.
But there's basically two differences with ITT, is that we have an actual type of propositions, whereas in ITT there are several types. Each time I add an existential line above one level. So that's the basic predicative, and the other is that I had a tool to implement unique choice test mathematics. Maybe I just took time to formulate it that way, but in a certain sense I had it in mind from the beginning. I needed to separate some things. So if I had worked in ITT, then I would have been probably a bit sad.
Or some people do use the sort type or set for their propositions.
Yeah.
So my question is, what problems would you have run into if you would have tried that?
I would just have less help from the computer. I would have to be much more careful about how I'm writing things. And I typically like the computer to help me doing things he's good at helping me. Just if you do have the intro, you have to know for every single of your proofs whether you want to use it or not, and whether you're using it or not. When I was writing the matrix example from earlier, at some point I did something wrong. I destructed a bit too many things, and I asked technically Coq to compute more things that it should, and just yelled at me, and I was cool with that. Okay, so otherwise I would have made a terribly inefficient program and never knew why. It's still a bit messy. There's a lot of different types, so the program is still hard, and it's easy to make a small mistake. Okay, so I like to give the computer the opportunity to tell me what I'm doing wrong, and
So
that's the reason.
Did you write a letter to Martin-Love explaining that he was wrong?
I didn't, and I won't. First, he won't believe me. Second, he wouldn't care about my use case. It's not his motivation, I think, and his approach or approaches, because it varies with years, I think are perfectly legitimate, just not for my application.
Thank you. So on page 81 you mentioned the internal language of the tuple. And it's possible to use, so you would like to use the language of dependent type theory as a language for setters. Do you have some throwaway remarks on this? And you say it may be feasible.
Yeah, but there's
could you elaborate on this? So it seems that you had more in mind than there's actually in the thesis.
No, it's pretty much what I wrote. I mean, the two main problems is first we have to write this to be able to write in this language. So it needs to have some practical things like binders that work and that are actually useful. Not too much boilerplate. And the other difficulty I think was the fact that families were represented by arrows over the index. Which is the usual way to do that in category, but doesn't really play well with how we think of them and how we want to implement them. It's smooth for example, but it also means that we cannot have a category with pies, but no sigmas, for instance. And that is not very convenient to work with. Also, lots of boxing and things like that. They don't really want to happen, and that will just make things more difficult. Apart from that, there's plenty of small issues that have to be thought of, and a lot of work to be done. So I think principally, it's being able to write an actual guest language, embedded language inside Coq, and reformulate topos slightly, or quasi-topos in this case slightly, so that they play better with type theory. So I don't know how hard it is. For now, at least it's past my due differences.
Thank you. And the last one, which is again related to what Claudio said. So Claudio suggested to have the classical logic in prop. There's a recent suggestion by Peter Axel, which is in line with Tottle's theory, where you can reinterpret the propositions. So Peter Axel has a, I don't know whether you're aware of his logic-enriched type theory?
No.
Okay,
Oh,
so
I think I've seen
let
it.
me try to rephrase it. So there's a possibility not only to add the double negation to prop by having the double negation monad, but you can use other monads. There's a body of literature on this.
Yeah. That's like unification, isn't it?
It's the same as duplication.
Okay.
Do you think that it would be practical to use COP as a logic-enriched type theory?
I have to know more about it.
Okay.
I have no idea.
Yep. Time for more questions? So I've worked a bit with your machine integers, and this was actually very nice, so thank you very much for this. We have an implementation of real numbers, and we managed to speed it up by a factor of 100 by using your machine integers, so we're really very grateful for this. This is very nice. Now there's a rumor, let's call it a rumor, that your previous implementation of the machine integers, or in the process, you were able to prove false in the using the machine integers.
Oh yes, some points.
So I think I've seen the code, but I would.
Is it still possible?
That's my question. So how do we know? how do we know for sure now that it's no longer possible?
Well, you cannot
Is it
know
safe?
for sure. First of all, you can prove false in COP with a little help from cosmic radiations. It's not very reliable, but that can be done with a bit of effort. A lot. The other thing is there are and there will be mistakes in the implementation of COP. Hopefully as little as possible. But today I believe that the implementation was correct. We've proved a lot of things with respect to other things, but there are still parts that are only penetrable proved, and it's as possible as I said, not much. But it's all enough so that we can hope that test will be sufficient.
So where does it go from here? Will we be able to have a full foreign function interface in COP, or?
I think
steps in this direction?
Benjamin Grégoire is working on these sort of things, but Chantal will know more about it than I do. You should ask her later. And so it seems that it's getting quite realistic now that my implementation will be trashed and that will be replaced with something that is the heavyweight way, which is which is much more work, but has a few advantages in certain use cases. And well, maybe alone, that's the feature you asked, and also partially formalizing things like floating point numbers. Though I've been told that there are complete effective implementations of the IEEE norm in COP. Yes, no? Yes, okay. So you could use that and compile them to real floating numbers as well.
No, one more question? So on page 57, you talk about your work on E-bars. You mentioned a possibility to get a great performance boost out of this by moving this towards the kernel. Could you elaborate on that?
I'm not sure it would be a great performance boost, but it would help at least not checking the same thing several times. The idea would be to have in the kernel an abstract interface to unification and refinement. So that everything, the fact that it's unified means that it has to be trusted. So suppose we trust it, everything we do, when we refine a term, we always get a word that term, and when we unify it to variable, we always get unified things. There can't be bugs in the results, there can be bugs in the process. And the idea is that doing that, building the proof incrementally doesn't need an ultimate type check when the proof is done. And which could be faster, and maybe a lot. I don't know, we have to try. Because tactics type check a lot already. Actually, most tactics type check, and they verify that they're doing something right. But then the untrusted code, untrusted code, and so at the QED, we check that again. And that's sort of not very nice, or not very happy.
Just to be sure, I assume you know that a term that has been refined does not need a check.
Yeah, that's the point. No.
No, I think it doesn't need.
Yeah, but
so you really need to extend.
Yeah, but the idea is that we always keep the unification problem. So when you get a wrong unification problem at the end, you have to throw out the term.
No, it's not a matter of unification problem. The point has to do with positivity conditions.
Oh yeah, so you
need to extend. You would really need to re-engineer the information associated to meet a variable.
Yeah,
the sequence is not sufficient.
Yeah. Well, you might also want to check only the guard conditions and so on at the end, and check what's checkable incrementally, which is usually what technical do. But of course, yeah, there's plenty of small issues. I don't think it's such an impossible approach.
More questions? I'm going to. Thank you.
André?
On veut parler français?
Bien sûr.
Super. C'est pour commencer à tester la qualité du français du Pétran. Donc, ça m'intéresse les limites de coque. On va parler peut-être un peu des limites de coque. Donc, sur ce problème que tu as bien expliqué, enfin, tu as mis le doigt à un endroit bien précis dans l'exposé. Il y a quand même des gens qui prétendent faire des propositions avec, tu l'as vaguement mentionné, il y a certaines sortes d'égalités qui ont été même certaines inventées pour mieux franchir ces obstacles-là. Quel est ton verdict par rapport à ça? Quand tu as essayé et tu es formel, ça ne peut pas bien marcher?
Ça dépend. Disons que c'est difficile. Alors, la réponse, elle peut être assez longue. Sorry, I'll swap to English maybe. And I'll restate the questions.
Ça y est, t'as dit 3 phrases en français, ça va. C'est pas mal.
So the question was about all the variants of equality that could be used to work around the problem I showed in the slide. So the question is last. First, at this point, I'm working with an equality that is a set equality, that is an arbitrary equivalence relation. So this doesn't really play with other things like I know, the first answer we could give, for instance, would be to think about Pierre Scrib's work, where he gives a way for Koch to unify things that are probably equal when this stays decidable. In particular, we could give this Koch modular theory, as he calls it, the theory of monoliths, and get something that works here, but only for a special case. Not any monolith, but something that is a monolith for the propositional equality of Koch. That made a lot of effort not to use during the thesis. And so that will be
Excuse me.
Yeah.
For efficiency reasons?
Uh,
For the same reason for which you exclude the choice principle?
Not entirely. It's because it's a really complicated construct, and it has a very bad property that I can actually eliminate on the proofs. I can compute using the proofs of equality, which is something I don't want to do. So it breaks my typing. Prop has leaks in a certain sense, and I wanted to avoid that. And also for conditional reasons, it seems a bit wrong. But in particular, it gives a structure of set to everything, including category. It was very useful throughout the work to have categories that were not sets in any manner of speaking. I didn't want to have equalities of objects. I wanted to state it precisely isomorphisms I had chosen. So that's the reason for not using a predefined universally natural equality. But I see you're not convinced.
I don't know. I wonder why you dislike. What did you say you wanted to avoid? That the categories being a set. Why
Yeah.
not? Why not?
Well, in certain cases it's good, in other it's not as much.
Especially if you could have a hierarchy of sets.
The idea is that we'll have a set, and then we'll have a category, and then we'll have a by-category, and that makes a hierarchy. And that's far more better for controlling efficiency and things. It gives, I don't know, it's, I don't think I'm ready to argue for that today, but it's, it helps formulating things in a way that is closer to programming practice. Well, there's many little reasons, no strong reasons. And actually, using modes with respect to the propositional equality would be sufficient for all particular case, because Z can be represented in a canonical way, and quite reasonably so. So we could do that. So this would work in corporate theory. That's one answer. With a weaker theorem, it's still good enough. A second answer is to think about heterogeneous equality or dependent equality. Well, again, since we have types whose equality is decidable, intentional equality is decidable, so we could do that. But I'm seeing two basic problems. The first one is rewriting, and the second one is rewriting, but with a slightly different tone of voice. So the first one, so we have a good rewriting machine in Coq, but I'm not really sure it would work very well with it would work very well with a dependent equality or any variant of it. And most of the time I'm doing a lot of reasoning by rewriting. Maybe it wouldn't matter here. I don't know, I haven't had time to test everything I had in mind, and there's probably a few things to investigate here. Though of course it restricts, again, the kind of monoids I can use. But if it at least made this project true, that would be nice. And the other reason why I'm scared of that is because rewriting is usually not quite enough for this sort of problems. What I haven't said is that the file that contains the program for finite dimensional kernels compiles in 15 minutes. That's very long, and that's before this machine started to die, so that must be more than that. So that is because I never had the time to finish a reflexive tactic that would do the job. Rewriting gets pretty slow when there's a lot, and reasoning in pre-abundant category in particular is all about equational reasoning. It's all about rewriting. There's lines of rewrite, And we want to do that. With a reflexive tactics instead. So it's already pretty annoying to write a reflexive tactic for pre-abelian category because we have to deal with the types. There's a more recent technology introduced by Thomas Brevant and Damien Pousse, who used a notion of retyping. So they take, so for a monoid, for instance, you'd say that the reflexive representation of a monoid is basically a list, and then you insert types in it to make it a category. That uses the K axiom, I think. So I was a bit reluctant to introduce new axioms in Coq. So that's one problem, and it would be. I don't know how. I don't even imagine how hard it would be with something like that, where types are heterogeneous. I have no clue where to start to do that. So this is another big problem.
May I propose the next question so that you go ahead with the same ideas? Could you mention, since you were stuck somewhere, could you mention a natural benchmark regarding homological algebra or so, to test whether there is enough progress in Coq in the future, in the, say, 2 to 5 next years?
Well, we could.
I mean, I would like a statement, a mathematical statement in homological algebra that you would like to be proved in Coq.
Well, I had a few. One of them included a cone on a very small chain complex. So we could compute a couple of things about polynomials. Usually, that's the idea. That's the sort of benchmark we had in mind, computing properties of polynomials on zeros or whatever. I'm not. I didn't work on that very much because I wanted to focus on trying to streamline the process of getting to chain complexity in Coq. I thought it was somewhat more interesting at the time for me. So I have a few examples in lists, but I haven't studied them very well. So I can't really recall the precise details here. But yeah, there are plenty of examples that are available right away. And we could do that at least in a non-graded case. Some of them would work, I guess. Yeah, that's not very satisfying answer.
Non, c'est ok.
C'était encore une
Non, oui, si j'ai le temps, mais tu as l'air de dire oui en pensant non, donc ça va, ça va. En fait, il me semble que Serge Gérard, il faisait de l'homotopie, non?
Un petit peu, mais c'est surtout l'homologie.
Oui.
C'est ça, surtout l'homologie avec une couche pour monter au niveau homotopique.
Ah, donc tu considères que c'est vraiment un niveau de difficulté, que c'était...
C'est déjà beaucoup plus dur à certifier parce que c'est pas des algorithmes qui sont exacts. Enfin, c'est des algorithmes qui vont donner des résultats dans certains cas. Il faut spécifier des cas, mais je ne connais pas très bien. Et sur le coup, c'est un truc que je maîtrise pas. La théorie derrière cette reconstruction des homotopies.
Parce que ça se vend mieux quand même, l'homotopie en concurrence et tout ça, l'homotopie dirigée, ça existe. Et
Ah oui, c'est pas loin d'ici.
Hein?
Oui, non, mais oui. Oui, mais c'était pas. Enfin, le but n'était pas tant de certifier des trucs qui vont servir à certifier d'autres trucs, d'autres programmes, puis d'essayer de s'intéresser à cette théorie et d'essayer de construire des choses jolies dessus.
Oui, mais alors pourquoi avoir mis toutes ces contraintes idéologiques du type pas d'axiome du choix?
Non, pas d'axiome du choix, c'est pas une contrainte idéologique, c'est une contrainte pratique. On ne peut pas avoir l'axiome du choix dans une catégorie d'ensemble à la Bishop. En fait, il y a, pour prouver qu'on ne peut pas avoir l'axiome du choix et que des fonctions qui calculent, j'ai utilisé le fait qu'on a un type des propositions, c'est un ensemble des propositions, je pense. Donc c'est un petit peu plus fort que de dire qu'on a une catégorie d'ensemble à Bishop en général. On pourrait peut-être l'avoir dans une catégorie où on n'a pas un ensemble des propositions. Ce que je peux prouver, c'est que de toute façon, les catégories d'ensemble à la Bishop avec c'est la chose dans un topos. Le topo c'est booléen, donc 1 plus 1, c'est 1 plus 1, ça devient un objet classifiant. Et comme c'est un objet classifiant, bah, tu peux, ce que tu dis, c'est que en gros tu peux décider la validité des propositions.
Mais ça c'est pour le choix, c'est pas pour le choix unique.
Ah oui, pour le choix unique. Pour le choix unique, c'était une façon pratique, encore une fois. C'est parce que ça m'aidait à écrire des programmes efficaces.
Merci.
All right.
Maybe in English. Carry on now, we tested your question. So, yes, first thing is, I think it's a very, very good idea to start from work, because clearly like the proof system technology is ready for that. And on the other hand, the question, I mean, this is what you is to tackle.
It's not ready.
Yeah, because I will have a question in the end, yes, about your paid.
Yeah, go on.
Yes, the last one. And also, in a way, his work or his school is maybe not so strongly accepted, I don't know, in mathematics, so in algebra, okay? And so the question is whether we can help, in a way, to defend or advocate these effective techniques, yes, in mathematics. And so, from that point of view, the fact that you have, I mean, on the one side cock and the other side category theory, I don't think is by chance, because in both situations of formalization or categorical algebra, the first thing we do is not look at the proof as it is, but try to, and the vernacular proof, but try to redo it, to do it in a more clever way so that it's adapted to your language. Okay, so like for instance, if we do, for instance, just clearing this work, the first thing you do is you try to think about how to formulate already the property. Yes, and then, and in category theory, because there is all these diagrammatic things, essentially it's about algebraizing arguments which apparently are in a higher logic. Yes. So from that point of view, it's quite striking in your thesis that you rediscover ideas. I think, okay, so in some cases you took them, so it's like the question is coming yet. Is whether you rediscover them on the way, or you took them from the literature and it made sense. Because, okay, so like typically the definition like of, this view of categories and by categories and stuff, but below there is this sets, okay, which are some kind of omega, I mean, categories enriched over booleans, omega. Yes. Is it something you devised? Because the same idea came in, like for instance, if you look at Bayes-Dolan hierarchy, they have the same picture.
Yeah, so
is there any influence because it's not mentioned in the
Yeah, I haven't. Yeah, of course. I actually read some of their proposals, and it was it was a bit influential in the way I formulated things in the manuscript. But mostly, I sort of. Well, I discovered the ID, and then because I was starting to understand that I moved. I went to read a bit about it and see that it could be, well, that many of the IDs were already there and some additional, because I never thought of the fact that we could consider the set of proposition as sort of a -1 category. Well, it makes a lot of sense now. It's something I discovered there, but it's not really relevant for the discipline. I mentioned that somewhere in the manuscript.
Yes, but it's not just in that case. So, for instance, your notion of okay, at some point you look at topos and you're not happy because they have this unique choice property. So you say, okay, I will move to quasi topos. So is it something that you look at in the literature and you?
Not at all, actually. So there's an anecdote here. I was in Spain and giving a talk about this. Mathematics without any choice, though I wouldn't say that way at the time. And I mentioned in passing that we didn't have a topos of sec. And Eduardo de Hook was in the assistants, and he was really unhappy with that. And he's the one who came up with the funny. He told me about qualitative thing.
Because maybe something which is worth mentioning is that so in the typical construction of the realizability topos, which is it's somewhere it's around here. Yes, it's topos based on realizability, so on computation functions. You start from a tripos and you build a topos. Yes, but it's very natural in the middle to have something like a quasi-topos. My student Jonas Frey, he developed a theory, and in the middle, it's not a quasi-topos, he calls it topos. But the point is, when you have this quasi-topos, in order to get a topos, it's exactly the unique choice axiom, yes? So you take so-called coarse objects. The coarse object, so you have this big thing, and the coarse object is an object which satisfies in some sense. So this unique choice property. And then you get the topos, and that's the way the realizability topos is constructed. Interesting. Okay, so that's what I enjoyed, so there is this of course efficiency aspect and so on, but it looks like you kind of rediscover in your own way basic concepts like this. Even if Dubuc, as part of that, it's a good sign of some kind of correspondence. Because I think one aspect of this formalization is what kind of mathematics is adapted to it. And I think there are many options. There is not, but and then yes, I have a question about your last.
This one or this one?
Yes, the last slide, the painful one.
Painful one. This one?
Yes, this one.
Pain. Oh, right. Yes. So the last one.
Yes. So if you look at your last, it's really depressing. Like you fail to apply it to cup. Imagine someone who comes in the room and says, oh, "Really? Okay, and I thought that cup could do that kind of thing." So my question is there you moved from topos to quasi-topos and you're happy with that? So is there a way? So for instance, the fact that you have this associativity problem, yes? FGH and FGH. So in many situations we will say, okay, maybe we need to check. And the problem is the type in which you live, yes? Because it's not the same.
Yeah.
Yes. So then you would say, okay, I would like to have an action on the type. And so could you relax, if you like, in some clever way, the theory of graded categories, so in such a way that this would work?
I don't think so.
Okay, so do you think it's
not straightforward. There might be tricks to make it work, but I don't think there's any weaker variant of graded category that will work straightforwardly.
But you cannot imagine any notion of coercion between the two types?
You can do coercion. The problem is that they will appear deep in terms when you have F composed with G composed with thing composed with P1 plus P2, pi2 and identity and thing. So you have types everywhere, you have coercions everywhere. Yes. You could make them push them up, etc. But that would make things much more complicated. Yeah, I don't think it's strictly speaking impossible. I think it's impractical.
Yes, but that's the point. Okay. So if you think about bicategories, they are heavily syntactic in a sense, because every time you do something like associativity, you need a coercion. Okay, so it's crazy. But there are coherence theorems which say that you can forget all this extra data.
Yeah, but the coherence theorem would bump into the associativity nightmare once again, because there's associativity between coherence flows as well. And this is the same problem again, I think.
Okay.
I'm not sure.
Because you see, in some situations, when you realize things, you can forget information. So in a way, coherence forgets maybe this extra.
Yeah. No. I don't think it's possible, but you might prove me wrong.
No, but you agree that it's a serious thing here.
Yeah, I think
it's really basic.
Yeah, but I like to see that in a more optimistic way than you do. It's a very big challenge to see what should be changed in Coq. So that's more my point of view on it. So I wouldn't be so depressed.
Yes, so the point is you want to change Coq. Is that you?
Oh yeah, just throw dependent types away.
I don't know. It's just The question of what dependent types are, I think, is still yet unsolved, and there's plenty of things to discover about them. And well, I hope we'll have exciting results in the next, I don't know, 10 years. I hope, maybe. And in fact, maybe someday it will be very easy to make that work. And that would be wonderful.
So I have the very last question, and I'm happy. Yes. So, page 85, yes, at some point. So maybe just our clarification, and then, so you say at some point, because we are back to the problem the discussion we had earlier about what is a category, yes? Yeah. So I think it's fair to say, well, we have objects and there is no equality on them. Yes, that's
the most general version of it.
But then the question is, what is a natural transformation? Yes? This is the way you define, and you say phi is parametric.
You don't have the main version of it.
Yes, I'm in the old version. Yes, sorry. No, but
I was talking about, yes, here I am, yeah.
Yeah, so you have a little diagram, and you say, okay, it's parametric. So,
yeah.
so my question is, it's a more general question, in fact. So here, you say it's parametric, it's not a bit informal, and you understand what it means, but...
yeah, that was an informal way of stating it, but you can write it diagrammatically.
But my question is, do you think it would be possible to embed all the things you're doing in a semantic? Yes. Where, like topos, but some kind of extension of topos, where you could then fine-tune, and see. Because for the moment there is some kind of, okay, you have mathematics, then you have the cog system, yes, and then there's an interaction between the cog system and the mathematics. But all this is not formalized inside a larger universe.
So you imagine a three-step approach. You say you have cog, you define a generic universe in it, like I don't know, topos or two topos, and you work inside that two topos to work all this out.
I think like so like you would build a model of I don't know, CCI or something like that, and then everything you're doing in your thesis you could formulate it inside, so you know what it means. So for instance, what it means to have no object, no equality on objects.
We have school clash here, I think, but
because you mentioned about the axioms, yes. So for instance, now currently people speak about the univalent axioms and work, okay. And it's all about plugging, interpreting the whole system inside some mathematical universe, and then checking that you're like internally building
something that makes sense. But I think that there's much more value to computation in itself to give meaning than it would appear on first sight. But I don't really like the model approach to give meaning. My point of view of models, rather than they help understanding structure about the object. My object of study is not a model, it's coq. And I think that's way enough. There's a lot of meaning inside coq. Computation is sort of in a certain sense the source of all meaning in mathematics. That's how I see it. So
the problem is that coq remains an undefined notion, okay? Because so you want to have, like programming languages, it's good to have models for them. Yes, so
it's good to have models, but that doesn't mean it's the models give them their meaning. That's my point. And there's we could work into a subset of code that has a well-defined model. That way we had a lot of new things appearing, I guess. But I'm not really interested by this idea. It's not that it's uninteresting per se, it's just not for me. It's not the sort of thing I do. But I know we'll have many heated discussion about that, and we already had so.
Okay, that's fine with me. So we start with some kind of tension.
It's cool slash. It just happens. It doesn't matter. Okay.
Benjamin.
Écoute, je ne vais pas poser vraiment de questions, ou pas trop en tout cas, parce qu'on a eu suffisamment d'interagir. Je vais quand même faire une remarque, c'est que je me suis rendu compte par cette occasion, alors d'une part à quel point la richesse de ton travail, je pense que tu aurais pu occuper non pas 2 mais 3 ou 4 directeurs de thèse, comme la variété des travaux que tu as fait ces dernières années. Et puis aussi, mais là ça je me suis rendu compte juste maintenant, c'est à quel point tu es têtu, c'est-à-dire que tu as réussi à travailler, et non seulement à travailler, mais à me convaincre de te laisser travailler sur les 2 sujets qui me semblaient les plus dangereux, qui sont d'une part la question des variables distancielles en coque, et d'autre part de reposer sur une formalisation avec beaucoup de types dépendants.
Oui, mais
Donc, je fais partie des gens justement qui se méfient beaucoup de ça, et là tu as réussi à me convaincre que si c'est ça qu'il fallait faire. Bon, cela dit, alors tu as réussi à survivre, ce qui est un mérite des félicitations supplémentaires. Bon, mais en même temps, il y a quand même ce truc qu'on n'arrive pas tout à fait à faire ce qu'on aurait voulu sur ces complexes de chaîne. Et je vais juste poser la question, est-ce qu'on est d'accord sur ce truc-là, que finalement, parce qu'on a quand même ce code Lisp,
ouais.
et on voudrait le prouver. Alors est-ce que la conclusion c'est que finalement, est-ce que tu es devenu lispien à la sortie de ta thèse, ou est-ce qu'il n'y aurait pas eu un moyen de le faire, de s'en tirer avec plus de vérification dynamique, avec moins de types en fait? Donc est-ce que le truc qui frappe là, c'est que finalement on ne sait pas, est-ce qu'il faudrait plus de types dépendants, avec plus de coercion, les relations, etc. Mais on n'est même pas sûr de qu'est-ce qu'il faudrait, ou est-ce qu'au contraire il ne faudrait pas, si c'était à refaire, est-ce que j'aurais raison de dire non, surtout pas de type dépendant, on se débrouille, on fait autrement, quitte à le faire un peu à la liste avec. Ou est-ce qu'il faut le faire en PVS?
Avant de répondre, une remarque, c'est que je suis au moins pas le seul à t'avoir convaincu d'utiliser le type dépendant, parce que c'était vraiment l'idée de Thierry à la base. Donc j'étais pas tout seul, vous avez pas fait si fort.
C'est quand même méritoire parce qu'on a avant, on n'a pas réussi.
Et donc, ce que j'ai essayé de dire, je pense, ma conclusion à moi, c'est qu'on a trouvé une bonne façon d'organiser les maths, et que si on a une bonne façon, et la programmation, et que si on a une telle bonne façon, tout langage qui ne me laisse pas faire ça, eh ben, il est limité de cette façon. Alors on peut se dire, il y a toujours une analyse entre les limitations et les bénéfices. C'est normal. On peut se dire, je suis prêt à payer ce prix-là pour avoir autre chose. Mais c'est souvent intéressant de se dire, finalement, qu'est-ce qu'on paierait comme prix de réussir à lever cette limitation. Donc ça c'est plus ma réponse à la question. Ensuite, est-ce que c'est mieux de trouver en 2 morceaux séparés avec le code d'un côté et la preuve de l'autre. Ça justifie parfois, mais je dois admettre que simplement les nouvelles possibilités de programmation qui apparaissent quand on se balade avec plein de structures à l'intérieur des types, c'est assez remarquable, un peu addictif même. C'est-à-dire que c'est vrai que tant qu'on sort pas je sais pas, quand on est un programmeur Java, on dit à quoi ça sert les types d'ordre supérieur, parce qu'on n'en a pas besoin, parce qu'on ne l'a jamais utilisé. Et puis quand on les utilise un jour, peut-être que c'est bien plus difficile de retourner à Java. Et j'ai un peu l'impression que quand on fait ça en 2 phases, on sait plus qu'on est en train de se battre contre une limitation du système et se dire bon, on va faire dans ce qu'on arrive à faire. Et pas tant qu'on a trouvé. Parfois c'est la bonne solution. Je pense que sur un développement assez long, ça devient de plus en plus intéressant d'avoir des maths au milieu. Mais encore une fois, ça dépend du développement. Dans celui-là, je trouvais que c'était vraiment, ça se justifiait vraiment.
Écoute, merci en tout cas, je te félicite encore d'apporter là.
siège du président du jury, je crois que j'en ai avoir une toute petite et j'espère que la réponse pourra être assez rapide quand même. Dans le travail sur les variables existentielles, quelle est la motivation la plus forte? L'efficacité ou une meilleure...
pas du tout l'efficacité.
Une meilleure capacité à expliquer ce qui se passe?
Non, c'était pas ça, c'était juste... j'avais des preuves à faire et j'en pouvais plus traquer, de refabriquer mon machin, de fabriquer mon ensemble séparément en utilisant le programme, de redescendre, de refaire mon... il y avait des moments, il y avait des variables existentielles qui apparaissaient au milieu et qui étaient difficiles à résoudre, en particulier quand je faisais des preuves sur les groupes abéliens à un moment, qui ont été vraiment pénibles. Et donc il y a un moment dans le stade de mon écriture de preuve où j'ai craqué, je me suis dit c'est plus possible, j'implémente ça parce que j'en ai marre. Voilà, c'est tout.
Y a-t-il des questions dans la salle? Bon, pas de questions. Alors, nous avons c'est dans le fond, c'est ça?
Si c'est difficile de fermer ce que je veux, c'est que devant nous, on va notamment.
Non,